Welcome students, we are starting our study on definite integrals. Now before we could add on to understand the concept of definite integrals and then pursue further on by doing various problems, it is imperative we need to understand integral calculus. So the question is why? Why do we need to have integral calculus? Now we all know that there are several geometrical shapes. Say for example, I take the shape of a square and it has a side of s units. Now the area of this square is going to be side into side. In other words, it's going to be equal to s squared. Now say for example, we have a rectangle and the area is required, and we have this side to be the breadth and this side to be the height, and we would want to get the area of this rectangle. Then that area would be b into h. We can also call it as either breadth into height or width into height. So both ways you can make the representation for the rectangle. Now after the rectangle, let us see the parallelogram. So we got a parallelogram and you would want to know the area of this parallelogram. Now the width is b and the height, so whenever we are obtaining the height for the parallelogram, we would obtain the vertical height in this fashion, right? So the area of this parallelogram would be equal to b into h. Now let me go to the triangle. How we would obtain the area of the triangle? Say imagine the vertical height is h here and the base is b units, and the area is half times b into h. Now let us go to the trapezoid. Now the trapezoid is a quadrilateral and its shape is something of this fashion, and if this h is the vertical height and if this b is the base, then there is one more width here, so we should also take that width. Say let us give that width as a, since we have taken b here. So the area of the trapezoid is going to be sum of a with b divided by 2 multiplied with the height. Now let us take the circle, one last area. Now this is a circle. Now you want to find the area of the circle, we would need what is called as the radius, and the area is going to be pi r squared. So all of these shapes are symmetric. In other words, these are all defined shapes, right? So that is the reason we are able to take the sides and then we are able to obtain a formula for that. Now the most important question here comes is, what if I had been given something which has got no defined shape? How am I going to obtain the area? Now you might be asking why finding the area is important. Now look around yourself. Everything is a physical representation of the human mind. In other words, any shape that you see, be it a house or a palace or a mansion or a monument or an architectural building of great importance to the culture, everything is built on shapes. Without shapes, there is no representation at all. So to get that shape, you would require area. In other words, if tomorrow you wanted to build something of importance to represent your culture or the traditions that you have got, you need a monument. monument in mathematical term is called as a geometrical shape. Now to construct the geometrical shape, you need measurements. In other words, we call it as dimensions. Now dimensions can only be achieved or can only be obtained if the shape of what you are in mind as a perfect geometrical representation. Say you want something in form of a square or a rectangle or a parallelogram or a triangle or a trapezoid or a circle. And there are other figures also which I have not represented, which have a perfect symmetry and a perfect formula. But what if you want something which is of marvel? When I say marvel, I mean something which is unique in nature. Now, if you want to do something or create something unique in nature in form of a shape, then you need something different or something away from these formulas. And only then you can call it unique, right? Of course, you might, there might be claim that we don't have to, but if you are confining yourself to these predefined shapes, then the representational structure is going to be a predefined shape. That's it. But the urge to create something of different becomes more stronger with the creative mind. So what if you want to create a shape of this fashion? So that's the basic question that has been posed by great people with the mathematical bent. So you got the x-axis, you got the y-axis, and I would want to have a shape something of this fashion. Now to bring this shape into existence, as I mentioned to you, we need dimension. I need to know how much area that this particular shape occupies. The basic way you can say this is what? This is a curve and you got an area that is below the curve. That is the utmost representation that you can say. Say for example, it starts from A and it ends at B. And there isn't anything further available as of the area is concerned or the concreteness of the shape is concerned, so that we can associate the shape to one of the things that we have just seen here or other things which have predefined structure or symmetric. So the requirement is to obtain this particular area. So what are we going to do? Now what the mathematical bent people of those days did is that they thought, okay, why not I associate this particular shape to a symmetric shape that is well known. That was the idea they had, right? So always what exactly we do is to solve any complex problems. To solve a complex problem, we relate the complex problem to an easier problem that was previously solved. And then we take in inputs from this particular solution and try to break the problem into finite parts. So this is the general way of solving complex problems. So that is exactly what they did. So the idea is that they created a rectangle. So this went on like this, and this was the shape that they created, and they called it as a strip. So this rectangular strip that has been created will have a width. So the width is taken as dx, and dx is the most important point. This is a very important point, is negligibly small. That's the idea here. Now because dx is negligibly small, this region that you see here, which flows out of the curve, is neglected. So this is neglected. Now this is the concept that is being applied here. Now why did they neglect it? Because dx is already negligible small. Okay, so having mentioned that, so this region which we see that is overflowing outside of the curve is neglected, and with dx being the width, we would like to know the corresponding y value, and that corresponding y value is given by y is equal to f of x. So the area that we see is a rectangular strip, and that area is given as width. You can call it as width or breadth, width multiplied with the height. So what exactly is the width here? The width here is dx, and what exactly is the height here? It is f of x, and we write it like this: f of x times d of x. So this is the area, but apparently the curve is flowing from, or the required area is from point A to point B. So to get that required area from point A to point B, what exactly they did is that they divided all the regions that is below this particular curve into rectangular strips. So you got a rectangular strip like this, and then this is a rectangular strip, and then this is the rectangular strip. So it kept on, the division went on up all the way until they reached the final end. So you got multiple strips, and you're expected to find the area of the region from A to B. So how are we going to represent? The representation was like this: S. So this is long S. So S stands for sum, the summation of the area of each of these rectangular strips has to be done from A to B. And what are we going to sum? We would have to sum f of x times dx, and this is what is called as the area under the curve. And this is the whole idea of definite integrals. So I hope you understood the concept why exactly we need definite integrals. So now we head on to understand the f of x that is seen here and how exactly we are going to evaluate this. So the evaluation is as follows. So to define f of x, we need this particular criteria. F of x that we see here should be continuous and defined on a closed interval a comma b, right? And when that happens, we state the following: integral a to b of f of x times dx is equal to capital F of x. The limits are a to b, and we substitute the limits as f of b negative capital F of a. This is called the lower limit, and this is called the upper limit. And this would give us the area that we need. So that is the in brief understanding of definite integrals. We will move on to do questions related to that. Now students, let us see how to evaluate a definite integral. Now this is the first example that we will do here to understand exactly how the execution of definite integral is performed. So the question is, integrate a certain function with the limits 3 to 8. So this is the lower limit, upper limit is 8. The function given is sine of root of x positive 1 divided by root of x positive 1 times dx. Now what is the understanding? Now this is actually a function. So in other words, this is a curve. You remember I have given you a shape of a curve like this. So this is actually some curve, and we are expected to find the area under this curve with the starting point being 3 and the ending point being 8. So the a and the b are being given. Now to evaluate this, we would follow the same process that we had followed for executing indefinite integrals. So what that means? It means that we would have to first start off by using technique of substitution. So I would take x positive 1 to be equal to t squared because of the presence of the square root. To differentiate this, I would get dx is equal to 2t dt. Now there are two ways that we can integrate this. I'm going to be showing you both the ways. Now let me show you the first way. The first way is as follows. So in place of root of x positive 1, I have to substitute this. So this one would give me t, because x positive 1 is t squared. Square root of that would give me t, divided by, I have t here, and dx is 2 times t dt. So let me place that 2 over here and t dt. Now if you see, I have not placed the limits at all, so don't do that. This is the first method, so let me write that down. Method 1. Now clearly you can cancel the t that you see here, and this would give me 2 times integral sine t dt. Now if you were to integrate sine t, integral of sine t is going to be negative cos t. Now what you got to do first and foremost is take this negative sign out. So it's going to be negative 2 times cos t. But what is t? Now from here, t is nothing but root of x positive 1. So revert back to the original variable. So in this case, substitute root of x positive 1 in place of t. So this is what we have got. Now place the limits 3 to 8. And then you can use the word APL or applying the limits. It's not necessary, but we are going to be applying the limits. So that is going to give us negative 2 times of, I apply the upper limit, I get cos root of 8 positive 1 negative cos root of 3 positive 1. This is what I would have, or this is what I'm getting. Now this is equal to negative 2 times cos of root of 8 positive 1. This is 9, so root of 9 is 3. 3 positive 1, that's 4. Root of that is going to be 2. So in this case, it's going to be cos 2. Now bring in the negative sign. If I were to bring in the negative sign, this is going to be 2 times cos 2, because this is positive. Not necessary, but just to have a clear look. And that is followed by negative 2 times cos 3. So this is what we have got. Now what we can do to get the method 2. Now another important thing, you don't have to add positive arbitrary c, because the limits already have taken care of that particular arbitrary c. So you don't have to do that. So this is the final answer. Now let me just show you method 2. Now as for the method 2, there is no particular change when it comes to evaluating it, but there is a change when you apply the limits. Now in this case, if you see here, I have taken x positive 1 is equal to t squared. So there are a few things you need to do, and that is called as change of limits. So this is the concept, change of limits. Right. Now why are we doing change of limits? Because the variable is changed from x to t. So when x is equal to 3, we will have to find out the value of t. Now we would be using this t. So t is equal to root of 3 positive 1, that's equal to root of 4, that's equal to 2. So when x is equal to 3, the value of t is 2. And when x is equal to 8, the value of t is 8 positive 1, which is equal to root of 9 is equal to 3. That's all. So when you are writing here, so this would mean, now 2 times, you add this, right, 2 times integral sine t dt would be now having a limit which is stretching from 2 to 3. And if you were to apply the limits, after integrating this is going to give me negative cos t, and the limits are 2 to 3. I take the negative sign out and then apply the limits. Cos of, you will have to apply the upper limit. So the upper limit is 3, and that has to be followed by the lower limit. Always we have a negative sign here. Now this negative sign should not be confused with this negative sign. I've already taken that negative sign out, and this is going to be cos of 2. So if you were to take the negative sign inside or distribute it, this one would give me 2 times negative is positive, so it's going to be 2 times cos 2, negative 2 times cos 3. So clearly if you were to compare the previous solution to the solution that we have just obtained, they are both one and the same, right? So the idea is you can either follow this technique or you can follow this technique, and there are only 2 ways that you can apply, either method 1 or method 2. So it's up solely at your discretion what method of application that you would wish to follow. So having mentioned that, let us go on to do other questions. Students, we have been given this beautiful question. Let me state the question. If alpha is equal to integral 0 to 1 e raised to the power of 9x positive 3 times tan inverse of x times 12 positive 9x squared divided by 1 positive x squared times dx. So this is a quantity of this fashion, where tan inverse of x takes only principal values. Then we are expected to find the value of ln modulus 1 positive alpha negative 3 pi over 4. So foremost, what I wish to do is I would like to consider the given question. Consider integral 0 to 1 e raised to the power of 9x positive 3 times tan inverse of x times 12 positive 9x squared divided by 1 positive x squared times dx. Then what I will do is I will use the technique of substitution. So I'll start off like this. Let 9x positive 3 times tan inverse of x be equal to t. I differentiate this, I get 9 positive 3 times differential of tan inverse of x is going to be 1 over 1 positive x squared times dx. This is equal to dt. I take the LCM as 1 positive x squared. I would get 9 positive 9 times x squared positive 3 times dx is equal to dt. This is equal to 9 added with 3 would give me 12 positive 9 times x squared divided by 1 positive x squared times dx. So this is what I would get, and that would be equal to dt. So now we can clearly see that 12 positive 9x squared times dx divided by 1 positive x squared is already available here, and I can rewrite this as e raised to the power of 9x positive 3 times tan inverse of x is t, and this entire quantity is dt. Now the limit comes into play. Now what are we going to do? So I would be changing the limits using the method that I've just mentioned. So for that, let me use the space here. So I will want to get the equivalent limits for t. So when x is equal to 0, my t is going to be 9 times of 0 positive 3 times of tan inverse of 0. So this is going to be t is equal to 0, right? When x is equal to 0, clearly you can see that t is equal to 0. Now the next step comes when x is equal to 1. What happens to t? Let me write that down. T is equal to 9 times of 1 positive 3 times of tan inverse of 1. Now this is equal to 9 positive 3 times tan inverse of 1 is pi over 4. So this is what we get. 9 positive 3 pi over 4. So the limits are 0 to 9 positive 3 pi over 4. Now if I were to integrate this, this is going to give me e raised to the power of t, with the limits being 0 to 9 positive 3 pi over 4. So I substitute the upper limit, I would get e raised to the power of 9 positive 3 pi over 4 negative e raised to the power of 0, which is nothing but e raised to the power of 9 positive 3 pi over 4 negative 1, because e raised to the power of 0 is 1. So this is what we have got. And what is this exactly? If alpha, so this quantity is nothing but alpha, right? So we have got alpha is equal to this. So let me move this 1 to the left side. So this would mean I get alpha positive 1 is equal to e raised to the power of 9 positive 3 pi over 4. Now let me take ln on both sides. So this is going to be ln of alpha positive 1 is equal to ln of e raised to the power of 9 positive 3 pi over 4. Now we know that ln of e, because e and ln they get neutralized. So this would give me 9 positive 3 pi over 4. Okay, so this is for the ln. But we are expected to find the ln of 1 positive alpha negative 3 pi. So therefore I can state here ln of, you can either write it as alpha positive 1 or 1 positive alpha is equal to, in fact I should have placed this negative, so let me just place this negative sign. So it's going to be negative 3 pi over 4 is equal to, for ln of alpha positive 1 I can substitute 9 positive 3 pi over 4, but there is a negative 3 pi over 4, so substitute. So what do you see here? So clearly 3 pi over 4 can be cancelled, giving me equal to 9. So this is the value, and we have achieved it in a beautiful fashion. So that is the completion for this question, students. We will move on to the next question. Students, we are given this question. F of x is equal to 7 times tan raised to the power of 8x positive 7 tan 6x negative 3 tan 4x negative 3 tan square x, and x is given to be an element present between the interval negative pi over 2 and pi over 2. We are expected to integrate integral 0 to pi over 4 f of x dx. So we need to know what is the value for that. So what I wish to do is, foremost I would like to consider, as always we will start off by consider the given function f of x is equal to 7 tan 8x followed by positive 7 tan 6x negative 3 times tan raised to the power of 4x negative 3 tan squared x. Now I will club these two together, and I will take 7 out, and I will take tan 6x out, tan raised to the power of 6x. So this is going to give me tan squared x positive 1. I'll take 3 out and tan squared x out. So that is going to give me tan squared x positive 1. Now clearly I can take tan squared x positive 1 out, and that is going to give me 7 times tan raised to the power of 6x negative 3 times tan raised to the power of 2x. But we know that secant squared x negative tan squared x is equal to 1. So from here secant squared x is equal to 1 positive tan squared x. So if I were to take this as 2, therefore I can rewrite 2 as 7 times tan raised to the power of 6x negative 3 times tan raised to the power of 2x times tan squared x positive 1 is going to be secant squared x. So I will use this in, say, let me take this as 1. So therefore I can rewrite 1 to be as integral 0 to pi over 4. F of x is now this 7 times tan raised to the power of 6x negative 3 times tan squared x times secant squared x times dx. Now if I were to take, let tan x be equal to t, I differentiate this, I get secant squared x dx is equal to dt. I get a secant squared x dx, and of course I can make the substitution for tan x. Now comes the important point. So what happens to the limits? So when x is equal to 0, what happens? T is equal to tan 0, which is equal to 0. And also when x is equal to pi over 4, t is equal to tan pi over 4, which is equal to 1. So therefore if I were to take this as 3, therefore I can rewrite 3 as, with this substitution, is equal to integral, the limits are 0 to 1, 7 times t raised to the power of 6 negative 3 times t raised to the power of 2 times dt. So if I were to integrate this, is going to be equal to 7 times t raised to the power of 7 over 7 negative 3 times t raised to the power of 3 over 3, the limits of 0 to 1. Now I'm not going to cancel anything now, so I just substitute the limits. So upper limit minus lower limit, so it's going to be 7 of 1 raised to the power of 7 divided by 7 upper limit negative 3 over 3 1 raised to the power of 3. So this is the upper limit, followed by minus the lower limit. So the lower limit 0, 0, 0, everything is 0. So you don't have to even substitute. So now this is going to be equal to 7 over 7 negative 3 over 3. And what happens here? 7 and 7 gets cancelled, 3 and 3 gets cancelled. You get 1 negative 1 is equal to 0. So this would mean integral 0 to pi over 4 f of x dx is equal to 0. And this is a good place for us to draw the red line. So this is a beautiful question, and we have achieved the solution. So we will make sure that we have understood the concepts and the application part, and now we will proceed on to the next question, students. Now what if instead of asking to obtain the integral from 0 to pi over 4 f of x dx, the question was asking you to obtain the integral from 0 to pi over 4 of x times f of x dx? How would you handle this question? Now this is easy for the fact that we have already deduced or simplified f of x. Now f of x from the previous simplification is nothing but, in fact, let me write it in this fashion: 7 times tan raised to the power of 6x negative 3 times tan squared x times secant squared x. So this was the simplification that we have achieved for f of x. So I'm going to use that. So if I were to use that, I can rewrite this required as follows. So integral 0 to pi over 4 x times f of x dx is equal to integral 0 to pi over 4 x times, so this is 7 times tan raised to the power of 6x negative 3 times tan raised to the power of 2x times secant squared x dx. Now we need to use integration by parts. So we know the formula. It's going to be uv negative integral v du. So we will have to make the suitable choice for u and for dv. So what I would do is I will take u to be equal to x. So this would give me du to be as dx. and my dv to be equal to 7 times tan raised to the power of 6x negative 3 times tan squared x times secant squared x dx. Now if we were to integrate this, this is similar to integrating this, right? And what did we get? We got this representation first, and we are going to be using this representation, and from here we will get the value of v, right? So what I would do is I would have to get the value for v. So let me get the value for v. So if we are going to be using this representation, what would be the situation now? So this is exactly what we would get, right? So if I were to rewrite this, this is going to be t raised to the power of 7 negative, in fact 3 gets cancelled, so this is going to be t raised to the power of 3. But my t is tan x, so therefore this would mean my v was going to be tan raised to the power of 7x negative tan raised to the power of 3x. So this is what I would be having here. So let me write that down. So v is equal to tan raised to the power of 7x negative tan raised to the power of 3x. I've already shown you how to integrate this. I'm just using the result from the previous question. So this substitution is going to take the following form. So my u is x, my v is tan raised to the power of 7x negative tan raised to the power of 3x. Now the limits, let me just write that down. The limits, I'm not done any change of limits because the original variable is present here. So just write down the limits. The limits are from 0 to pi over 4. Now that is followed by negative integral. My v is tan raised to the power of 7x negative tan raised to the power of 3x times my du is nothing but dx. And the limits for this is going to be 0 to pi over 4. So that's what we have got. So now what I'm going to do is I'm going to rewrite this in the following fashion because we need to get the evaluated part, right? So take the tan raised to the power of 3x out, so that would give me tan raised to the power of 4x negative 1, right? So I've got a tan raised to the power of 4x negative 1. Now the idea is I need to split this. So how I'm going to split it? Now this can be split as follows: integral tan raised to the power of 3x. Now this is similar to a raised to the power of 4 negative 1. I can write it as a squared negative 1 times a squared positive 1, right? So that's exactly what I'm going to do. I'm going to rewrite this as tan raised to the power of 2x negative 1 times tan raised to the power of 2x positive 1 times dx. Now we have seen a formula, right? So let me draw your attention to that formula. So what is the formula did we see? We know that secant squared x negative tan squared x is equal to 1, and from here 1 positive tan squared x is secant squared x. So I would be substituting secant squared x here. So it's going to be negative integral tan raised to the power of 3x times tan squared x negative 1 times secant squared x dx. So if I were to make the substitution for tan x, if I were to take tan x is equal to t, this would give me secant squared x dx is equal to dt. So I can rewrite this as negative integral t raised to the power of 3 times t raised to the power of 2 negative 1 times dt, which is actually equal to negative t raised to the power of 5, I need to integrate this, followed by t raised to the power of 3 times dt. So if you were to integrate this, this would produce me negative of t raised to the power of 6 over 6. So I'm reverting it back to tan. So tan raised to the power of 6x over 6 negative tan raised to the power of 4x over 4. So this is what I've got. So on the left hand side I've got this, right? So what I will do is I will use this space here. So this is going to be equal to, so this is equal to x times of tan raised to the power of 7x negative tan raised to the power of 3x, the limits of 0 to pi over 4, right, followed by negative of this part, what we have just got. This is going to be tan raised to the power of 6x over 6 negative tan raised to the power of 4x over 4, and the limits are 0 to pi over 4. Now when you apply the limits, just make this observation. When you apply the upper limit, this is 1, right? Pi over 4, tan pi over 4 is 1. Doesn't matter what the power is, still you are going to get 1. This is 1, so 1 minus 1 is going to be 0. Upper limit vanishes. Now the lower limit is 0. So if you were to place 0 here, everything becomes 0. So this is gone. Similarly, upper limit is pi over 4. You place pi over 4 here, followed by, you will have a pi over 4 here. So we will have to evaluate this. So let's see what the evaluation leads us into. So upon substituting pi over 4, this is going to be giving me tan pi over 4 is 1. So this is going to be 1 over 6. This is going to be 1 over 4. Now we will have to evaluate this. I will show you the evaluation over here. I know the space is a little bit constrained. Now the LCM for 6 and 4 is going to be 12. I got a negative sign, so I'll place that over there. 6 divides 12 2 times, so I place the 2 there. 4 divides 12 3 times, so I place the 3 there. So 2 negative 3 becomes 1. I got a negative sign here. So this is equal to negative, in fact 2 negative 3 will give me a negative 1, so I'll place that there, divided by 12. So what happens? Negative of negative, that is going to give me positive. So I'll box this here and I'll write this as 1 over 12. So that's a solution. I hope you got the gist of it. So the value, what is the value we are asked to find? What is integral 0 to pi over 4 x times f of x dx, and that is equal to 1 over 12. And we can draw the red line here. So that's the solution, students. If in case they have asked this, then we will have to evaluate, we will have to execute this in this fashion, and we will move on to the next question. Now students, we will have to know the properties of definite integral. Now the first one is integral a to b of f of x dx will be the same as integral a to b f of t dt. So in this case the variable is x, and in this case the variable is t. So the outcome will not matter. So we will get the same outcome. So property number 2, integral a to b f of dx. In other words, integral a to b f of x times dx will be equal to negative integral b to a f of x dx. If you were to change the limits, we need to counter, or we need to make sure to accommodate a negative sign. Now the third important property is integral a to b f of x dx is rewritten as integral a to c f of x dx positive c to b f of x dx. Now the integral is actually split. The reason for the split is because we are encountering a point of discontinuity. That is the reason. So suppose you have a graph like this, say this is A and this is B, and the graph is stretching from A and it hits a point of discontinuity, and there is somewhere over here the graph again starts. and then it is heading towards B. So clearly there is a point of discontinuity at C. So we will have to accommodate that point by splitting the integral in this fashion. So we will have to look into problems of this nature to have a better understanding. So let me demonstrate this concept using an example. So we are expected to integrate this quantity, integral 0 to 3. This is the greatest integer function. Now if you were to draw the graph for the greatest integer function stretching from 0 all the way up unto 3, then you will make the following observations. So let me just split it as 1 over here and 2 over here. Now graphically, if you were to represent this greatest integer function, the function will start, it will head up to 1, and at 1 it will break. So there won't be any continuity after 1, so there is actually a split here, and the function will again start off from 1 and then it will head to 2, and at 2 there will again be a split. Now let me just write down these points so that you can better associate it. So 0, and this is going to be 1, and this is 2, and further down you have a point 3, right? So there is a discontinuity at all integers. So that is the important observation we will have to take into consideration. So at 2 there is a discontinuity, and the function heads or starts from 2 and it moves to 3, and then at 3 there is a discontinuity. The function starts at this particular point and then heads to 4. So there is always a discontinuity at all integer points. Now if you were to represent this, how are we going to do that? So it's going to be integral 0 to 3, greatest integer function, and from 0 to 1, what happens? The functional value is 0, positive. From 1 to 2, the functional value is 1, and from 2 to 3, the functional value is 2. So this is how we represent the function. So this vanishes, and if I were to integrate this, I would get x limits are 1 to 2. If I were to integrate this, of course there is a 2 there, and you'll have to represent the 2 outside the parenthesis. So I'm placing the 2 here. So this is going to be x limits are 2 to 3. So this is going to be 2 minus 1 followed by 2 times of 3 minus 2. This is equal to 1. This is equal to 2 of 1. This is equal to 1 positive 2 is equal to 3. So this would mean integral 0 to 3 of the greatest integer function is nothing but 3 units. So this is the solution for the question, and we have executed it in a wonderful way, specifically with the representation of the graph. Students, we are expected to integrate this quantity, integral 0 to 3 modulus of x negative 1 times dx. Now whenever we are given modulus, we are expected to study the sign of the function. So for that we need to know the x value. Now we know from the definition of the modulus function, f of x is defined as follows. That is, it will open out or open up with a positive x for all values of x that is greater than or equal to 0 for this particular function, and it will open up with a negative x for all values of x which is strictly less than 0. So this is the definition we will be applying. So if I were to draw the graph for this modulus of x negative 1, the graph would look something of this fashion. So this is going to be 0, this is going to be 1, and somewhere down the line I got 3 here. So this is going to be when x is equal to 1, In fact, when x is equal to 0, this will be the hit. So the graph will flow up to this point 1 and it would again rise up, and this would be the rise here. So when x is equal to 3, the hit would be 3, negative 1, 2. So this point is going to be 2. Right. So the region that is required is this. This is what they want us to find, the area of this particular region. So how are we going to find the area of this particular region? So therefore, let me fix the question. Integral 0 to 3 modulus of x negative 1 times dx would take the following form. For values which are between 0 and 1, because at 1 the graph is hitting the axis. So 0 to 1, as I mentioned to you in property 3 of the integrals of definiteness, we need to split the function. So 0 to 1 would be one quantity and the other one would be from 1 to 3. So the question is, what would happen to the function in this particular range 0 to 1? In 0 to 1, the values of x, we need to study the function for all values of x between 0 and 1. So for all values of x that are actually falling on this side, we will have to open up with a negative x. So the modulus of x negative 1 would open up with a negative sign. That's what I exactly meant. So that would be negative of x negative 1 times dx. And for all values which are on the other side, which are greater than 1, greater than or equal to 1, we would have to open up with a positive sign. So it's going to be x negative 1 times dx. So we will have to integrate this. So this is going to give me negative of x squared over 2 negative 1 times dx. That's going to give me x. So the limits are 0 to 1, positive, this is going to be x squared over 2 negative x. The limits are 1 to 3. You can't cancel any of these terms, but they are with their respective limits. So let me just write the evaluated quantity over here. So this is equal to evaluate. So we are expected to apply the limits. So we've already got negative of x squared over 2 followed by a negative x, and the limits are heading from 0 to 1 followed by positive of x squared over 2 negative x. The limits are heading from 1 to 3. So let me substitute the limits. The upper limit first is going to be 1 over 2 negative 1. So that's for the upper limit, followed by the lower limit is 0, positive, the upper limit, followed by the lower limit. So this is equal to negative of 1 over 2 negative 1 would give me negative 1 over 2. That's for this part, followed by 9 over 2 negative 3. 1 over 2 negative 1, that's going to be negative 1 over 2, and negative of negative would give me positive 1 over 2. So this is going to be 1 over 2 positive, and I can take the LCM for these two. So that would give me 9 positive 1. I'm just placing negative 3 as it is. So this is equal to 1 over 2 positive. 9 added with 1 would give me 10 over 2 followed by negative 3, which is equal to 1 over 2 positive. 2 divides 10 5 times. So 5 negative 3 would give me 2. So we've got 1 over 2 positive 2. Taking 2 as the LCM, we've got 1 positive 4, which is nothing but 5 over 2 units. So this would be the area under the curve or the function modulus of x negative 1. Now graphically also we can solve this question. Let me show that to you over here. Now if you would remember, or if you would just go back and review the video, the graph, I drew the graph for this function in this fashion. So 0 to 1 to 3, and this was the function modulus of x negative 1. When x is equal to 0, we hit the point 1, so the graph headed in this fashion, and when x is equal to 3, the graph hit the point 2. And if we were to join this is how the graph will look. So we expected to find the area. Now both the things are triangle. Now the area of the triangle is half times b into h. So if you were to take the area of this is going to give me 1 over 2, right? This is 1 unit. So this area is 1 over 2 times 1 times 1. So it's going to be 1 time 1, which is equal to 1 over 2. So this is this region. So we can write that down, 1 over 2. Added with this is 1 to 3. So this base is going to be 2 units, and this hits the point at 2. So this is going to be 2. So this area, if you were to calculate this area, it's going to be 1 over 2 of 2 base into height, which is nothing but 2 units. So the total area is 1 over 2 added with 2, which is nothing but 5 over 2 units. So graphically it appears to be quicker, right? So if you are given MCQ, multiple choice question, based on the function and the limits, you can adopt this graph technique. Of course, doing by definite integration is always advisable for the very fact that we may not always encounter simple questions. So having mentioned this, we will move on, students. Students, we are given a beautiful question. We are expected to find the value of integral negative 1 to 1 x squared times e raised to the power of the greatest integer function x cubed times dx. Now, as I mentioned to you, if you were to consider the greatest integer function for the interval negative 1 to 1, you will have to take into account that the greatest integer function will be discontinuous at all integer values. And in this case, it would have to be considered from negative 1 to 0 and 0 to 1 because of the discontinuity that would occur. And the interval for this would be split from negative 1 to 0, followed by 0 to positive 1. So in the first phase, the value of x that we would consider would be between negative 1 and 0. Now we would want to know what is the value of x cubed, the greatest integer of x cubed. So that is imperative to solve this question, and this requirement is needed. So if x is lying between negative 1 and 0, x cubed will also be in this particular interval, negative 1 to 0, because all I need to do is just cube it up. And if I were to take the greatest integer of x cubed, that would give me negative 1. And this in turn would mean e raised to the power of greatest integer of x cubed would be equal to e raised to the power of negative 1. So that is a very important point we will have to take into note. So this is going to be x squared times e raised to the power of, as I mentioned to you, this is going to be negative 1 times dx. Now coming to the next interval, 0 to 1. So x is lying between 0 and 1. So let me write that like this. X is between 0 and 1, and this would mean x cubed will be between 0 and 1, and the greatest integer of x cubed will be equal to 0. So this would mean e raised to the power of x cubed is going to be e raised to the power of 0, which is equal to 1. So in this case, it's going to be x squared times e raised to the power of 0 times dx, which I can easily integrate. So this is going to be, I'm rewriting it, integral negative 1 to 0 x squared times e raised to the power of negative 1. That's a constant, so it's going to be 1 over e times dx, followed by e raised to the power of 0, that's going to be 1. So I need to integrate 0 to 1 x squared times dx. So that's simple to integrate. this is going to give me 1 over e. Integral of x squared is going to be x to the power of 3 divided by 3. The limits are negative 1 to 0. This is going to be x to the power of 3 divided by 3. The limits are 0 to 1. If you were to apply the upper limit 0, the lower limit is going to give me negative 1 over 3. In this case, the upper limit would give me 1 over 3 followed by 0. So rewriting this, I get 1 over 3 times e positive 1 over 3. I take 1 over 3 out. I would get 1 over e positive 1. In fact, you can either stop here or you can go up to this particular point. So this is the solution, students, and we have achieved the value for this. So it's a beautiful question, and we were able to solve it because of the definition of greatest integer function. So we'll move on to the next one. Now, this is another important property that we will have to learn, which is integral negative a to a f of x dx is equal to, now most of the times you would say it is 2 times integral 0 to a f of x dx, but this is incorrect because of the fact that this will only happen if f of x is even. This is the requirement for this to take place. If not, it would be equal to 0. Integral negative a to a f of x dx would be equal to 0 if f of x is odd. So have that in mind. It's a very important property, and it will come in handy in solving questions of higher magnitude. When I mention questions of higher magnitude, it means questions of complexities. You would have to use integral or this particular property. Now students, I'm going to show to you that how exactly integral negative a to a f of x dx becomes equal to 0 when f of x is an even function. Now let us take f of x to be equal to sine x, and let us find out what happens if we had to integrate sine x between the interval negative pi to pi. Now if we were to draw the graph, this is 0, this is pi, this is negative pi. The graph would be something of this fashion. Okay. So this is the sine x wave curve. Now if we were to split this integral, say negative pi to 0, so let me just write this parent integral first, negative pi to pi sine x dx. This is going to be negative pi to 0, because at 0 there is a hit at the point 0 there. So that's going to be negative pi to 0 sine x dx positive 0 to pi sine x dx. Now let me just consider integral 0 to pi sine x dx. Now if I were to integrate this, I would get negative cos x. The limits are 0 to pi. I can take the negative sign out, and that would give me negative of cos x, limits of 0 to pi. I apply the limits. So applying limits is going to be negative of cos of pi, negative cos of 0. Now cos of pi is negative 1, cos 0 is 1, there is a negative sign here. So this is going to be negative of negative 1 added with negative 1 would give me negative 2, and there is a negative sign here, that's going to be positive 2. So what have we done? We have just obtained the area under the curve stretching from 0 to pi as 2 units. Now let me head to the curve which is stretching from negative pi to 0. So let me show that to you. Consider now negative pi to 0 of sine x dx. If you were to integrate this, this is going to give you negative cos x. The limits are negative pi to 0. Of course, I would be taking the negative sign out. So this is going to be negative of cos x of negative pi to 0, which is equal to, I substitute the upper limit followed by substituting the lower limit. So this is equal to negative of cos 0 is 1. Now cos of negative pi, that is going to be negative 1. So this is equal to negative of 1 positive 1, which is equal to negative 2. So this is negative 2. Now if you would remember, we started with integral negative pi to pi sin x dx, and we split it as negative pi to 0 sin x dx positive 0 to pi sin x dx. We got the value for this as negative 2, we got the value for this as positive 2, and we got this outcome to be equal to 0. Now this is similar to integral negative a to a f of x dx being equal to negative a to 0 of f of x dx positive 0 to a of f of x dx. And the outcome that we received in this case is 0 because of the fact that we were dealing with f of x to be as sin x. Now sin x is the popular example for a function which is odd. Have that in mind. Now since f of x is odd, we got this outcome, and we just seen this outcome. So this would mean integral negative a to a f of x dx will produce 0 whenever we are dealing with a function which is odd. And the classic example of an odd function is sin x. Now the other probable question comes, what if f of x is even? What would happen if f of x is even? What would be the outcome? The outcome would be equivalent to 2 times integral 0 to a f of x dx. That would be the outcome. Now the much important question comes is, can we prove this? Of course we can prove this, and that is exactly what we would be doing now. Now I wish to consider this example. I'm going to take f of x to be equal to modulus of x, and I would like to know what happens if I were to integrate this function with the limits being from negative 1 to 1. Now foremost, if we were to draw the graph for this modulus function, the graph would look something like this. So this point is 0. If I were to take this as negative 1, this as positive 1, and I want to know the area, right? Now let me just integrate it, or apply the concept of integration. I'm not using graphical technique here. First let me go with the usual method of integration. Now for all values of x lying between, so this can be rewritten integral negative 1 to 1 modulus of x dx can be rewritten as integral 1 to 0 modulus of x dx positive integral 0 to 1 modulus of x dx. Now for all values of x lying at this lesser than, right, on this particular side, x, or in other words modulus of x, would open up with a negative sign. So this is equal to integral negative 1 to 0 negative x times dx. For all values of x lying between 0 and 1, the modulus would open up with a positive value. So 0 to 1 positive x times dx. Now let me integrate this. This is going to give me negative of x squared over 2 positive x squared over 2. The limits are 0 to 1. The limits are negative 1 to 0. So I will have to place the limits here. So let me do that. So if you were to place the upper limit, placing the upper limit here, so that's going to be 0 here, followed by a negative sign, and lower limit is -1, that's going to be 1 over 2. So the outcome is going to be 1 over 2 for this case, right? Now let me consider this one. This is going to give me 1 over 2, right? So 1 over 2 added with 1 over 2 will give me 1 unit, right? Now let me check the other probability, or I would say what happens if I were to rewrite. So let me use the space here. Okay, probably I will use this space. What will happen if I were to write integral -1 to 1 as 2 times integral 0 to 1 of modulus of x times dx? So in this case, clearly it's going to be 2 times of, this will open up, since the value of x lies between 0 and 1, this will open up with a positive x times dx 0 to 1. If I were to integrate this, this is going to give me x squared over 2, limits are 0 to 1. I substitute 2 gets cancelled, which is 1. So this is equal to 1 unit. And what did we get here? 1 unit. So clearly this is possible because of the fact that f of x is even. So that is the take home point. So we have seen 2 illustrations, and in first case f of x is an odd function, in the second case f of x is an even function, and because of the function being odd, the outcome was giving us 0, and because of the function being even, the outcome is giving us 2 times integral 0 to a f of x dx, and we have clearly seen it with some good examples. So we'll move on to the next